Hello everyone, welcome to In 5 Minutes. In this video we are going to see the next problem on beta function type 2. So this is our question. So if you see in this question, we have to show that this integration is equal to this term, and hence we have to solve this equation. So we have to prove this. Then after proving this, we are going to use this proof to solve this equation. Okay, we are not again going to solve this equation because here we have hence solved. So we are going to use this proof to solve this given equation. So here if you see, we have the limits from 0 to infinity, and beta of m comma n is then given by integration of 0 to infinity x raised to m minus 1 upon 1 plus x the whole raised to m plus n into dx. So we have to represent this equation in this form. So the numerator term is matching, and in the denominator we have 1 plus x, but here we have a plus bx. So we are going to substitute something. So we substitute bx equal to a into some other variable. Why we are putting bx equal to this term into t? So when we put bx equal to at, here we get a plus at the whole raised to m plus n. From these two terms we can take a common, and we will have 1 plus t and the whole raised to m plus n. Now this term is equal to a raised to m plus n into 1 plus t the whole raised to m plus n. So now if you see this term and this term, both this term are matching. That's why we put bx equal to this term into other variable. Okay, remember this. So x will be at upon b, then dx will be a upon b is constant into dt. After this, since we are changing the limits of integration, since we are changing the variable, our limits of integration will also get changed. So here we write initial variable, and initial variable is x and the new variable is t. X is going from 0 to infinity. When we put x equal to 0 here, we get t also equal to 0. When we put x equal to infinity, we get t also equal to infinity. So our new integration will become integration of 0 to infinity x. Instead of x, we are putting a by b into t. So a by b into t the whole raised to m minus 1 upon, and this term, the denominator, we have calculated it as a raised to m plus n into 1 plus t the whole raised to m plus n into dx. Dx is this term, which is a by b into dt. Now consider this term. We have a by b into t the whole raised to m minus 1. So this will be equal to a raised to m minus 1 upon b raised to m minus 1 into t raised to m minus. Okay, so we get integration of 0 to infinity. A raised to m minus 1 upon b raised to m minus 1 is constant. So we can write out of integration. So this term into t raised to m minus 1. So t raised to m minus 1 upon a raised to m plus n is nothing but, so a raised to m plus n into 1 plus t the whole raised to m plus n into a by b into dt. So now we are going to take all the a term together and all the b terms together. So consider a term. Here we have a raised to m minus 1. Here we have a. So a raised to m minus 1 into a is nothing but a raised to m. And in the denominator we have a raised to m plus n. So the denominator we can write as a raised to m upon a raised to m into a raised to n. So a raised to m and a raised to m will get cancelled, and we get 1 upon a raised to n. So all the a terms will be converted into 1 upon a raised to n. Now after this we will consider b term. Here we have b raised to m minus 1, and here we have b. So b raised to m minus 1 into b is nothing but b raised to m. So all the b terms will combine and we get b raised to m. And inside integration we have t raised to m minus 1 upon 1 plus t the whole raised to m plus n into dt. Now if you compare this term with the equation of beta of m comma n, both the terms are matching. Here we have x and here we have t as a variable. So this term is nothing but beta of m comma n. So our I is nothing but beta of m comma n upon a raised to n into b raised to m. So if you now see, this term is matching with this term. So left hand side is equal to right hand side, hence proof. So this is the one part of the question.